tired today. I have 3 hours physics lecture and I don't understand any of them.
Me too.
What topic did you have learned just now?
Magnetism, bro. It's a piece of cake. Magnetism is about.
What is magnetic field? Magnetic field is the region around a magnet where a magnetic force can be experienced. The field can be represented by drawing lines called magnetic field lines or magnetic flux. What is the source of magnetic field? First, a permanent magnet. Second, electromagnet. Third, current carrying conductor. When the electric charge is stationary, it is surrounded by an electric field only. When the electric charge moves, it is surrounded by both electric field and also magnetic field. Magnetic field has 2 poles, which is north and south. When the opposite poles face each other, it will produce an attraction force that make the magnet attract one another. We can also see that the electric field lines leave the north pole and enter the south pole of the magnet.
What are you talking about? We cannot understand anything. It's so theoretical.
Babe, now listen to me. Let me give you an example of magnetic field experiment.
When conducting a magnetic field line experiment using iron filing with the poles of 2 bar magnets placed beside each other, you can observe different patterns depending on the orientation of the poles. When north poles are facing each other, the magnetic field lines repel each other. The iron filing will arrange themselves to show this repulsion. You will observe that the field lines curve away from each other between the 2 poles. There will be a clear region between the magnets where the filing are sparse, indicating a repulsive force. The overall pattern will look like 2 separate magnetic fields that are pushing away from one another. We need to observe how the iron filing move and arrange themselves around the magnet. You should see the filings aligning along the magnetic field lines, creating patterns that reflect the shape and structure of the magnetic field. The iron filings become magnetized in the presence of the magnetic field, each filing acting like a tiny magnet, aligned with the magnetic field lines created by the round magnet. In water, the filings can move more freely and quickly align along the magnetic field lines due to the reduced friction compared to a dry surface. The filings will align in a pattern that illustrates the dipole field lines looping from one flat face pole to the other. You might see elongated loops extending from the top to the bottom of the magnet, showing the 3-dimensional nature of the magnetic field. The filings will form visible patterns that map out the magnetic field lines. With a round magnet, the patterns may show concentric circles or loops, depending on the orientation of the magnet. The filing will cluster more densely at the poles end of the round magnet, where the magnetic field is strongest.
Oh, now I understand. The name that I'm using right now is related to magnetism theory. How can you do that?
The magnetic field in magnetic nametags is a crucial element that provides the necessary force to keep the nametag securely attached to clothing without causing damage, ensuring convenience and durability in everyday use. The front and back pleats are held together by the magnetic force with the fabric of the clothing sandwiched in between. The magnets in the back pleat create a magnetic field which exerts a force on the metal or magnetic material in the front pleat. Typically, neodymium magnets are used due to their high magnetic strength and small size. Magnetic field is concentrated between the 2 pleats. The design ensures that the field is strong in the region where the fabric is held, providing a secure attachment.
That's true, Aziha. Another application in magnets in our daily life is used on magnetic fields.
Experiments rely on the phenomenon of ferromagnetism, which is the ability of certain materials to become strongly magnetized in the presence of an external magnetic field. In an unmagnetized state, the magnetic domains within the material are randomly oriented, resulting in a net magnetic field of 0. However, when the fringe magnet is exposed to an external magnetic field, such as the magnetic field of a refrigerator door, the magnetic domains align themselves in the direction of the external field. Once the fringe magnet is attached to the refrigerator door, it acts as a magnet itself, exerting a magnetic force on any ferromagnetic materials nearby. This force allows the fringe magnet to securely hold lightweight objects against the refrigerator door.